CPU can look quiet while LLM jobs pile up. KEDA reads Redis queue depth and scales Celery workers from the backlog, so capacity follows real work instead of misleading utilization. You'll walk away with a setup that reads queue backlog, chooses worker replicas, and holds scale down until work drains. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams run LLM calls inside background workers and watch CPU or memory to autoscale. That seems fine until you remember provider waits. CPU can sit idle while hundreds of requests queue behind a rate limit or a slow network call. The result is a false calm, then sudden backlog spikes that hurt latency and cost. Queue depth autoscaling fixes that by scaling on pending work instead of pod utilization, so capacity actually follows demand. Redis is a common Celery broker, and KEDA is a lightweight Kubernetes component that can read Redis list lengths and scale a deployment. At a high level, the idea is simple. Read the Redis list length for the Celery queue. Decide how many worker pods that backlog needs. Tell KEDA the threshold, the per pod target, and a cooldown. KEDA then adds or removes replicas to keep the queue near the target. The upside is more predictable latency and cost. The downside is extra system complexity and the need to keep queue names and broker settings aligned. We will build a small example that shows the chain end to end. You will see the live queue depth, push tasks into the queue, compute a worker estimate, push a KEDA ScaledObject manifest, and then tune the scale down cooldown so pods don't evaporate right after a burst. No deep Kubernetes mastery required. Just the idea that KEDA manages a deployment based on a Redis list length. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need to read the actual queue size from Redis, so scaling decisions are grounded in the real backlog. This snippet connects to Redis and reads the Celery queue depth. KEDA will later watch. CPU can look calm, while LLM work is blocked on provider I/O. So the first signal to trust is the backlog itself. The Redis client is created as R. The queue name is fixed as Q, and RLNQ asks Redis for the current list length. That list name must match the Celery queue you route work into. Otherwise, KEDA will scale from the wrong signal. The visible output shows the live queue depth, which is the auto-scaling input that matters. Reading depth is useful, but we also need to push representative LLM tasks, so the backlog can form and KEDA has something to react to. This example submits guarded Celery work onto the Redis queue that will drive scaling. LLM tasks often need safety checks before they ever touch a provider, so Answer rejects oversized prompts inside the worker code path. App uses Redis as the Celery broker, and answer.apply async routes each prompt into queue instead of relying on a default queue name. The short return body stands in for your real LLM provider call, so the autoscaling path stays visible. The output shows how many jobs were placed on the queue, confirming that backlog can now accumulate independently of CPU. Now that we can measure depth and create backlog, we need a small estimator that translates list length into a worker count and exposes activation behavior. This code turns Redis backlog into a simple worker estimate before creating the real KEDA object. The activation value is the quiet zone threshold, so tiny bursts do not immediately wake workers from zero. The target value is the queue length you are willing to carry per worker, and seal depth divided by target gives a readable version of the scaling idea. Increasing target reduces worker count and cost, but leaves more jobs waiting per pod. Lowering activation makes scale-up more eager, which can help latency, but may create churn. The output shows the computed worker need and the backlog beyond activation. With the estimate in hand, we create the KEDA resource that links the Redis list to the deployment, so Kubernetes can act. This snippet creates the KEDA ScaledObject that connects Redis queue depth to the Kubernetes worker deployment. The Kubernetes config.loadKubeConfig call loads cluster access. Then client.customObjects API sends the KEDA custom resource through create namespaced custom object. The trigger uses type Redis, list name from queue, list length from target, and activation list length from activation. So the manifest matches the backlog math from the previous step. Scale target ref points KEDA at the LLM worker deployment, while max replica count caps cost and blast radius. The output shows the created scaled object name, confirming the auto-scaling policy reached Kubernetes. After the scaled object exists, we should make sure scale down is friendly to the next burst. A tiny cooldown can create cold start pain. This snippet patches the live KEDA ScaledObject to make scale down less abrupt after a burst drains. LLM queues can look empty between retries, callbacks, or provider waits, so immediately dropping workers may add cold start latency to the next wave. API.patch namespaced custom object updates only cooldown period and leaves the Redis trigger, activation, target, and max replica count in place. A longer cooldown period favors latency stability and fewer pod churn events, while a shorter value cuts idle cost faster after traffic stops. The output shows the accepted scale down delay and worker cap, giving an incident-friendly confirmation of the safety setting. This toy chain maps directly into a simple production setup. The Redis list is your Celery queue. The worker deployment runs your LLM task runner. KEDA watches the same list and scales that deployment up and down according to the same math you previewed. 3 quick points to remember. It scales on backlog, not CPU, so it reacts to real pending work. Use this when provider waits or blocking I/O create hidden queues you care about. One caveat is extra operational surface. KEDA, Redis, and Kubernetes configs must match queue names and expectations. If you want to iterate, tune the target value per worker and the cooldown period together. Try a target of fewer items per pod for lower latency, or raise cooldown period for less churn during bursts, and measure end-to-end request latency on a real dataset of prompts. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.